Hello judges, we are team the Singularity representing Helios AI. Our project directly target SDG 7, clean energy, and SDG 13, climate change. The real world problems we are solving is the net positive energy flow in traditional solar tracker system. For example, on cloudy days, standard trackers blindly hide for the light, causing their motor to consume more electricity than the panels actually generate. So this inefficiency hurts the ROI of residential homeowner and the large solar farms. To solve this, we built a predictive AI-driven tracking system using Google technology. Here is how it works.
So this one is the UI for our solar panel. So the data of the weather is from the Google and connect to our Firebase. And below one, the live tracking. The figure will show the reference position of our solar panel to the sun and the moon. And below, this is the angle of the servo motor for the horizontal and the vertical. So by using the remote control, you can change between the AI mode and the manual mode. The AI mode will make the solar panel find the base position to have the greatest brightness. And for the manual mode, you can change the angle of the solar panel, so you can see the figure at here. And by using the blue button, you can change this value at our Firebase by pressing it, so you can see this one is changed. So below one is the data of our LDR sensor. So this one is show the light intensity.
Hi, my name is Wong Wei Xiang, and I will be responsible for making the hardware of the solar tracker. The 4 LDRs on the solar tracker detects the differences of the light intensity, and then the Arduino Uno R4 is used to send out command to turn the solar tracker towards the sunlight. As you can see here in the coding, these are all the constants and variables used in the solar tracker. And in the setup, there is the Wi-Fi connection as well as the sending data to the database coding in the setup. Next, the loop includes the reading of the 4 LEDs as well as the humidity sensor. And then there is also the solar tracker and check Wi-Fi function. And next, it also detects the Wi-Fi connection, and if Wi-Fi is connected, it will upload the data as well as reading the manual commands. And this is the function for solar tracker, which detects whether it is raining or not, as well as if it is under manual mode. If not, it will become auto tracking. And subsequently, this is the function for auto tracking, which includes all the calculations for the differences of the LDR, as well as the movement of the servo motor. This is the function to check the Wi-Fi connection. If the Wi-Fi is not connected, it will attempt to reconnect to the Wi-Fi. Next, this is the upload data, which will upload the data according to the codes in a string. And lastly, this is the function to read manual command. It will attempt to read the values in the database and then move the motor accordingly. And that's all from me for the hardware part. Thank you.
I'm the software and the AI lead for the Helios AI. My task was to build the cloud brand for our dual-axis solar tracker. So I started by setting up a Firebase real-time database. I designed a custom JSON structure to standardize our AI command, weather data, and the hardware sensor reading in real time between the cloud and the ESP32. The core logic is my Python script, which integrates the Gemini AI and the Open Weather Map API. The system analyzes the real-time cloud cover. If it is overcast, the AI intelligence will trigger the diffusion mode to maximize the energy collection. I also implement a history logging feature. Every minute, a snapshot of the system decision and the sensor data is shifted for the future efficiency analysis.
Okay, next is the SDG choice well justified based on the real world need. Yes, from the curve that I found, it showed that the static solar panel is low efficiency compared to the solar tracker, and it is proved with our Helios AI, which showed that our Helios AI showed that the solar tracker is increasing 45% efficiency gain compared to the static panel.